Hello, everyone, and welcome to the latest podcast edition of Reimagining Mobility. I'm here with Aaron Pulskamp. Aaron, you work for us in Fuel Cell Canada, where we develop fuel cell stacks. So maybe to start out with, tell me a little bit, what have you been doing as of late?
Yeah, happy to. Thanks for having me, Stephan. So we're out here in Canada in the Vancouver area, kind of the heart of where a lot of fuel cell development goes down. We are a group of about 45 people, and I get the honor of being the engineering and prototyping manager out here. So our job is to take customer requests for engineering of custom fuel cell stacks, hopefully turn those into a real life fuel cell stack that we can then test in our testing lab. We also do a significant amount of our own internal fuel cell design and prototyping for our own purposes. And we're doing that with, at least on my team, about 18 highly experienced engineers that kind of cover all areas of the fuel cell component development. I have guys that specialize in every component, including plates and MEAs, but we also have people who do failure analysis, CAD design, quality, prototyping, all the areas that you would think you would need to execute a fuel cell stack design.
Perfect. So when we go right away to the fuel cell stack design, and you alluded a little bit to all the different components, the membranes, again, lots of different components that I'm certainly not an expert in, but if you had to explain what are the 2 or 3 most critical components in a fuel cell stack, what would that be?
Yeah, so I think we would start with the MEA, the membrane electrode assembly. It is the component that carries the catalyst that makes the electrochemical reaction that then produces electricity for the fuel cell to work. So that's probably the one key component as far as what makes a PEM fuel cell unique. But in order for that to work, you have to have fuel cell plates. We call them bipolar plates. Their job are to get the hydrogen and the oxygen to that catalyst layer so the reaction can take place. They also carry coolant because fuel cell stacks are actively cooled. One of the byproducts of the reaction is heat. So the bipolar plates separate the MEAs, and then as you continue to stack those up, you create more and more power. That stack of plates and MEAs then needs to be held together with some sort of mechanical compression system. That way it can stay nice and sealed, and that the contact resistance, the electrical contact resistance between the components inside stays low, giving you the best power that you can. So I would say that those are probably the 3 most critical parts.
Okay. So those are the critical parts. I guess a lot of times the most critical parts are the most challenging parts, right? In a battery, for example, everybody talks about the battery cell. In reality, I believe too, the biggest challenge is thermal management in a battery. So there it may not line up with critical components being also the most challenging to design right, to get right, to assemble right, to prototype right, test right, whatever it might be. How is it in fuel cells? Is the components you just mentioned, are they all the 2 to 3 most challenging components to design, to maybe not design, but maybe to build, because of quality issues, because of small tolerances, whatever? Can you shed a little bit of light on that?
Sure. Yeah. I mean, you did allude to a lot of the things we think about on those components. Each one kind of has its own unique set of challenges. I mean, if you start talking about the MEA with the membrane in there, the membrane is only 10 or 12 microns thick. It's very, very thin. And so now you're dealing with, in sort of industrial assembly processes, very thin, difficult to handle membranes. So that in and of itself is a challenge. But the catalyst layer that goes on it is also quite thin, and it contains platinum. And platinum is what makes the reaction take place. So we want to make sure we take care of our platinum. We don't want it to to wash away or to break down or to get corroded in any way. So the challenge is design a catalyst layer that's somehow low on platinum, but also durable and gives you the power that you want. So that's where you get into a little bit of that electrochemistry, a little bit of black magic, where mechanical engineers like me can't always get their head exactly around it. That's where we have a lot of expertise and chemists in-house that can help us with that.
Okay.
And then if you zoom out to the bipolar plate, you know, the whole idea of fuel cells is how much power can you make out of the smallest package, power density, we call that. And so you want the plates to be as thin as possible. But of course, as they get thin, you run into problems with, you know, robustness, cracking, breaking. If they're metal, perhaps welding is a problem because you're welding very, very thin substrate, like 100 micron thick substrate. So there's a lot of challenges there in trying to make a plate that is durable enough or robust enough to handle the stresses of being inside the stack, but not so thick that you lose your power density. And then lastly, I would just comment on the maybe the compression system that holds it all together. This is the part that most people can relate to because you can see it, you can see how it works. It has springs and things like that inside of it. But I would say that the challenge there is it needs to be able to be an interface to the rest of the fuel cell system. So you have to make sure you consider what those interfaces are. And I would also say that it has to be robust in that, you know, our products are in cars and ships and trucks, and you think about shock and vibration and things like that. And you're essentially holding together like an accordion of cells into a block, and you don't want that block to shift or move through the duty cycle of the stack or the lifetime of the stack.
I learned just recently that hydrogen leakage is also a problem.
Yeah.
And that the way I at least I understood it is you're okay with a little bit of leakage, but there's a fine line between a little bit of leakage and then too much. Is that another major challenge? Or is it just kind of like, you know, we got it as good as we can and we can live with a little bit of leakage? Or is this constantly something you experiment and prototype as well?
Yeah, you nailed it there. Sealing is a very big challenge in fuel cell stacks. Because we have, you know, usually several hundred individual cells all stacked up, you need to seal hydrogen, smallest element on the periodic table, in every one of those cells. So you end up with, you know, potentially miles of seal length inside a cell, compounded with the cells are so thin that you don't have a lot of space for like a nice, tall, compliant, squishy seal that you would want, like around your door seal of your vehicle, right? We're talking seals that are maybe a 0.5 millimeter tall on one side and maybe only 20 or 30 microns on the other side. So maybe second to that is you can't use sealing materials that would potentially harm the membrane or the catalyst layer. So we know, for example, that silicone, a very common sealing material, does actually have a harmful impact to the stack. So we want to make sure we use materials that are fuel cell safe, and also through very smart design, try to get seal profiles that seal the best we can. If it leaks hydrogen, that goes right to the efficiency of the stack.
Sure.
And the customer's fuel bill. So we really don't want to leak hydrogen. We also don't want to leak hydrogen from a safety standpoint. Even though it tends to disperse in air very quickly, we need to be careful with that. You can handle leaking a little bit of air because we just use air from the atmosphere. But that also creates inefficiencies on the system. You know, your pumps or your compressors are working harder and things like that. So we try to be smart about it and keep leaks to the lowest feasible level that we can.
So is the leaking challenge then, so to speak, is that an area where we are still working very heavily on, or is it something that, you know, if something new comes up, a new material, you mentioned you can't use silicon. I mean, are we actively, or is the industry actively looking into something like this, or is like, you know what, again, we can live with it. We better focus on the membrane or the bipolar plates or on something else. Where is the industry really focusing, other than we're focusing on the entire power plant, but specifically to the fuel cell, to the things, where are we maybe, in your opinion, focusing the most on?
Yeah, I think from like an industrialization standpoint or reducing costs via volume production, every component needs the focus. But probably most around the MEA and the bipolar plates and the seal. So you're right there.
Okay.
What we try to do here is benchmark the latest and greatest from all the suppliers we can find as far as sealing materials, plate materials, CCM, catalyst coated membrane, which is part of the MEA, so that we try to stay on the leading edge of what is up and coming, and then think about how that will eventually be ramped up into high volume production. So like I would say at any given time, we have R&D projects going on, maybe 3, 4, 5 on every one of those components to try to think about what's next and how we reduce cost while improving manufacturability.
Okay. Let's talk a little bit maybe about raw materials in batteries, which is oftentimes, right, we pin batteries against hydrogen or fuel cells, which is better, what is better, more efficient, you name it, a constant battle. I think the answer is probably they both have its proper place. But when we talk about raw material on the battery side, clearly it's going to be a major challenge. Billions and billions of dollars invested last year alone or announced for new battery plants in the US alone, so in North America alone. Maybe few people talk about where do we ultimately get all this raw material together that these factories can actually produce batteries. Do we have a challenge with raw materials for any of these components that you need for a fuel cell?
I mean, I think the one that everybody thinks about is the platinum. That's still our main catalyst in the catalyst layer. Of course, people are working on several non-platinum options, which I don't know much about, but we do poke around a little bit in that research. The amount of platinum is not a lot. I wish I knew an exact number, but I think it's milligrams per cell.
Okay.
And the good thing about that platinum is after the life of the stack, it can be reclaimed and recycled. So really, I think the biggest challenge is reducing platinum while maintaining the same durability and performance that we currently have. That's where a lot of chemistry research takes place.
Okay. And in your prototyping, when you put a complete fuel cell stack together, how much do you rely on your experience in how to put this together? How much do you rely on maybe virtual and simulation tools? How much you rely on, I'm going to try, and if not, I'm going to go a different route? Can you give me a little bit of an idea of how you, specifically in prototype, not when we get into whatever production, right? When we do hundreds or thousands of them, but again, in prototypes, 5 to 10 or so, what do you heavily rely on that maybe is normal practice or maybe unique for fuel cells?
Yeah, maybe like, I guess if you zoom out, it's a fairly standard product development and prototyping process as far as how you would create a new thing. I guess for us, we're fortunate in that we can start a lot of our research at a subscale level, small coupons, material samples, things like that, start to vet materials as before we make any major investment in full-size stack components. And then as we build confidence, we can then scale up to what we call a short stack, which is the footprint of a full-size cell, but only a handful of those cells, not several hundred. And we can gain almost everything we need to know at that short stack level and save the investment elsewhere. So we do a lot of short stack builds and testing. I would say before we even get to that point, though, we do an extensive amount of modeling and simulation.
Okay.
There's probably 3 main areas of modeling and simulation I think we focus on if we were to break it down. The first one is FEA, very standard mechanical finite element analysis that you would do to test the strength of a component design. We do a lot of FEA in-house, but then we also leverage greater AVL Corporation to help us with maybe higher computing power when we need it. The same goes with CFD. When we look at the flow of the gases and the coolant through the stack, we can now model the flow of, say, hydrogen through an entire fuel cell stack, which is amazing information for us when it comes to plate design, for example. And then maybe the area where it's the most exciting and evolving is performance modeling of a stack. So using physics and first principles math to actually predict how a stack would perform before you build anything. And so we do in-house modeling on performance, on the degradation of the stack over time, hydration, current distribution, all these things that you'd be interested in before we even build anything. And through those three types of modeling, we're getting really good at quickly iterating stack designs because we're starting to see that when we do go to physically prototype and test them, the models are validated. So I guess I have more confidence than ever in our modeling capabilities and our ability to quickly go through the development process and get to that prototyping stage.
Okay, very interesting. If maybe as a last question, if I had to put you on the spot and say, what is the number one, in your opinion, key enabler to get what you mentioned before, the key measurement of a fuel cell is the energy density, right? What in your mind is the key enabler? Is it a better virtual validation or design capability? Is it different material? Is it more stacking up of plates, so even thinner and better material, or what? Just anything and everything that you think is the number one, in your opinion, key enabler to improve energy density?
Yeah, I think if you're having me pick just one, it would be right back down to that catalyst layer, the electrochemistry. That's really where I think we can move the needle quite a bit, improving on power density. But of course, we're always trying to make the stack thinner, cheaper, stronger, all of those things. But I think when it comes down to a lever where you can easily influence the same stack design, the catalyst layer allows you to do that. You could take the exact same stack design, put in different catalyst layers, and get completely different performance out of it. So really, that's where it's at, and I think where we see a lot of our suppliers as well working. And it's been a very good and quick progression on power density in the catalyst layer world, especially as fuel cells become more popular. We see more investment. That was historically always our problem, is we know what we want to get, we just can't get it because nobody's investing in it. But now we're starting to have access to those materials, those suppliers, those designs that we didn't have previously.
Yeah, maybe that leads me now to my truly last question then. We've been working on fuel cell stacks within AVL for, I think, 10 years now. Fuel cell and fuel cell stacks and the hydrogen-based, let's say, propulsion fuel desire or capability has been around. We've been talking about it for 20 years, right? In your opinion, Aaron, is now finally the time where we hit that, where we're past that plateau and really now seeing applications where we're actually truly gonna do it, not just, let's say, in prototypes or in small areas, but really go into the mobility space in not just one small area, but from stationary power to heavy duty truck applications, you name it. Is now the time finally?
Yeah, it is the time. And I think that's not just my opinion. We see the types of customers that come to us and the diversity of customers that come to us with real investment power as well, not just wanting to do a little science project. I think a lot of that has to do with, we have a pretty good understanding of the limitations of batteries at the moment. It was always like, well, let's have hydrogen be after batteries, the thing after batteries. And now we're in the battery world and we kind of understand what the limitations are. And they're very strong in some areas and maybe a little bit more limited in others. And so people are starting to understand, okay, for real, hydrogen does fit in this sector and that it's worth investing in. It's exciting for us because on one, we could talk to a customer who's in the marine industry, and then the next day it's a trucking customer, and then the next day it's a guy who wants to build a drone, all with fuel cell. So I really do, and I not just marketing speak. I really do think from a technical engineering standpoint that the tide is turning, and that people are finally seeing fuel cells as a complementary powertrain technology, not a challenge to battery. We in the fuel cell world didn't think there was a competition. We know that they need each other. And so I think if the industry embraces that as well, and they are embracing that, they'll realize that that's the case.
Yeah. So at the end of the day, we're really driving the mobility trends of tomorrow, today, and in your case, and with Fuel Cell Canada at AVL, definitely the fuel cell stack, which is obviously a big enabler or the key component if you want to make hydrogen work here. So thank you, Aaron, for your time, and thanks everybody for tuning in.
Thanks for listening to Reimagine Mobility Podcast. If you like this episode, please subscribe and tell a friend.